and a lot of the problems involve ideal gases, and there's expansions and contractions and things like that against constant pressure, or maybe isothermal or reversible, where the external pressure and the internal pressure are the same. And it's basically your job to use this equation and to figure out whether or not heat is flowing, what the work is that's being done as a function of whether or not it's reversible or against constant pressure. I haven't really worked as many examples as thoroughly as I would like to, and so my goal is for this weekend, sometimes I don't always meet my goals, but I'm going to try to on this one. My goal is to shoot some video and to just review a few problems. So we'll do adiabatic expansions against constant pressure, we'll do adiabatic expansions that are done reversibly, isothermal expansions, etc. And I'll just kind of map out the roadway for those. So look on the website and be ready to catch that video, because it should be very helpful for your current homework assignment. All right.
Could you try one of those other markers that doesn't look very good on the camera?
First
Yeah,
law,
that's
delta
perfect.
U equals Q plus delta. So that's where you start with all of those calculations. You've got some process, and there's work being done, maybe heat's being exchanged depending on whether or not it's adiabatic, and you have to derive expressions for the work and the heat and the change in the internal energy. And go ahead.
You say you're going to post the homework solutions and everything online? Like for homework, for example, you post something for that. Just as like a study tool.
The thing is that a lot of those homeworks were borrowed from a professor who did this class previously, and I wouldn't want to just simply post the answers without his permission. So I'll send him an email and I'll ask him if that's okay to post them. Office hours, that's a great place to go to find those. And yeah, I'd like to say that I could shoot video, but the thing is, I'm shooting video for the rest of my life if I go through all the homeworks. Let me email that guy and find out what he says. I can probably give you the answers. I can tell you what the answers were to the problems and let you go back and grind them through, or just make a little notation on your actual. If you got the problem wrong, maybe make a note on the homework and point you in the right direction.
All right.
Is the video going to be on YouTube or the website?
It's on YouTube, and I'll send you links. I'll post the links on the website, so there'll be a Word document that you open up, and there's the link to the video, so you can copy and paste that into your browser and get to the video that way. Have you guys found the videos?
Yes.
I start watching them, and then I just get freaked out and turn them off real quick, because I hate the way I look and sound on camera. Freaks me out. Okay, so let's try to get started. We on Tuesday discussed this concept of enthalpy as a state function, and we said that the cool thing about enthalpy as a state function is that we could look at changes in that state function, and the changes would be equal or equivalent to the amount of heat that was released in a constant pressure process, right? And state functions are very nice because the calculations that you need to make to move from one state to another end up being independent of path. You can move from one state to another through a variety of paths, but regardless of which path you take, the value is always the same. And we're going to see some examples today of why that is such a cool process. Before I get into any calculations, I want to prime you for what's in your text. Hopefully you've been taking a look at your text. If not, you should certainly read the text. It's absolute. It doesn't go through the same derivations that I go through in lecture, but certainly it gives a lot of good qualitative information about these things. And one of the things that the text does is it breaks down a bunch of different processes and it tells you, what the enthalpy is associated with different things. It goes through ionization. It talks about the enthalpies of ionization, phase changes. So if you go from solid to liquid, from liquid to gas, what is the enthalpy associated with that process. Obviously, we have enthalpies associated with actual chemical reactions. And I just want to remind you that largely what we're talking about when we talk about the heats of a reaction is simply the energy that is associated or with a change in kind of the electronic state of matter as it goes from one state to another. So the enthalpy of ionization is simply the amount of energy, the amount of heat, energy in the form of heat, that's associated with moving an electron from its bound state on the atom to a place where it's gone, right? And we know what theoretically what the nature is of that energy. It's simply that whole force distance thing that you have to go through when you separate a positive charge from a negative charge, right? So the enthalpy of ionization is the energy associated with trying to push those two guys apart, right? And similarly for a phase change, when you go from the solid state to the liquid state, the enthalpy, the energy that you need to do that, is the energy that's associated with breaking those electronic interactions between molecules that are bound together in those states, right? You go from the liquid state to the gas state, there's some energy associated with that transition, and again, that's just the energy that is needed to pull those molecules that are bound together in the liquid state apart from each other and push them into the gas state. So the majority of the enthalpy that we're looking at is associated with those energies, right? There's energy associated with separating charge or bringing charge together. And then we also saw that there's a work function where if you're trying to conduct a process like this where you're separating one thing from another, but at the same time that system is being pushed down on by the outside environment, then you're going to have to push extra hard to separate them, right? So the enthalpy largely is this. It's that electronic interaction. It's the energies associated with different electronic changes. But anytime you want to have an electronic change like this, if you're under the influence of pressure from your atmosphere, from your environment, then you have to work against that pressure to make that change, right? So just kind of keep in the back of your mind that the bulk of the energy is that electronic energy, and then we've got that pressure volume term that also contributes, right? So the fact that enthalpy is a state function is really nice because we can just simply take the difference between the final state and the initial state, and whatever that difference is going to be the heat associated with that constant pressure process. And so theoretically, all you need to do to look at the change in enthalpy, to figure out what that heat is sum the total enthalpy of your products and subtract from that the sum of the total enthalpy of your reactants, and the difference is going to be that delta H, that Q, that's associated with the process. In this notation, we're looking at the total enthalpy. If you want to change that into a molar quantity, so the enthalpy per mole, then the calculation of delta H would have to involve the stoichiometric coefficients. So we have a partial molar enthalpy of any kind of a product or reactant times the stoichiometric coefficients in that sum. I'm sure you guys have seen this in your Gen Chem classes. We've done these calculations. The problem is that it's really difficult to know exactly what the total enthalpy content of any piece of material is, right? It's the internal energy, it's the pressure volume work that had to be done to get that thing at its particular state, and it's relatively difficult to break down a piece of matter into all of its different energetic components and its PV components. And so what we end up doing is, instead of trying to define a total enthalpy, which what we do is we take a path where we define a relative enthalpy. So if I were to ask you, what height are we at right now? you could tell me what height we were at relative to a number of different reference points. You could tell me what height we were at relative to a planet that was, 6 gazillion miles below us. How many miles away is the closest planet? I don't know. Is gazillion even a number? I don't know.
It's probably close.
The point is that when you ask about when you're looking at a value, you can use a value relative to a particular reference. We speak of altitude or height in terms of reference to sea level. For enthalpies, what we end up doing is we define an enthalpy relative to an enthalpy content possessed by the precursors, the elemental precursors to a reaction product in their most stable state at a particular, their most stable aggregation state at a particular set of conditions. And usually these conditions are 1 atmosphere of pressure and 298 Kelvin. And by definition, we take the enthalpy content of the reaction precursors, the elemental precursors, to be 0. So we say that the enthalpy content of elemental oxygen at 1 atmosphere of pressure and 298 Kelvin is 0. We define all reaction products that involve oxygen relative to that 0. So we define the enthalpy of formation of a compound as being the enthalpy of that compound minus the enthalpy of its elements, its elemental precursors. And this term always just ends up going to 0 because we're defining the elemental precursors to have a 0 enthalpy, right? And now we have this partial molar enthalpy of reaction to this reference state, or at this reference state, and our enthalpies of a reaction ends up being the sum of the standard enthalpies of the products minus the standard enthalpies of the reactants. Go ahead.
What's the point of like the bar over the?
That's per mole. I'm sorry, I should have.
Okay.
Totally. So we went from here saying the total enthalpy, right? And that includes multiplying those guys by however many moles we have. But now if we want to speak in terms of a partial molar enthalpy, we put that bar there, and now we say that the total enthalpy is the number of moles times the amount of enthalpy per mole of that substance, right? And this guy is the hard one to describe, and so we end up describing it relative to a reference state. And once we've described it relative to a reference state, that's when we put the big 0 up there, and that says, okay, so we're looking at that at a particular set of conditions relative to the enthalpy content of the elemental precursors. That's H naught of formation. And I should have defined this, sorry, I get ahead of myself. These enthalpies of formation are defined for producing the products at a specific state. So I told you that the elemental precursors, we take their enthalpy of formation as being 0 at some standard state, usually 298.15 Kelvin, 1 atmosphere of pressure. We also, we say that H naught of formation is the enthalpy associated with producing the product at some standard state as well, some reference state, which is usually 1 atmosphere of pressure, 298 Kelvin, right? Now, so you've seen tables like this before, right? Where they list the enthalpies of formation for a bunch of different compounds. C4H8, what is its enthalpy? It's negative 6.99 kilojoules per mole. You look up here, graphite is the standard reference state of carbon. It's the most stable state of carbon at 1 atmosphere pressure, 298.15 Kelvin, and it's got an enthalpy of formation defined as 0. So the elements in their standard states, the elemental forms of the compounds in their standard states, or the elements in their standard states, are assigned a 0 enthalpy, and everything else is assigned an enthalpy relative to that. So this is what we're talking about when we look at relative enthalpies. So here, we've got two compounds, or four compounds, that are composed of carbon, hydrogen, and oxygen. Right? We've got this propane and oxygen, we've got carbon dioxide and water. And if we want to define the distance or the magnitude of the enthalpy difference between these, instead of having to calculate straight across, we can speak of their relative enthalpies to their elemental precursors. So if the elements in their standard state are at 0, then propane has some, the combination of propane and oxygen has some enthalpy relative to that. Carbon dioxide and water has an enthalpy relative to that, and the magnitude of the change between the two is simply the difference between the two enthalpies. Does that make sense?
Yeah.
All right, so using that, calculate for me real quick what the delta H is between for the reaction with propane and oxygen to form carbon dioxide and water.
You just subtract them. It's negative, right? Should be negative. Out of the homeworks. Pass this sheet around, so go ahead and put your name on it for me.
anybody hear about the town hall meeting that's supposed to happen today, where we discuss the
Science building?
science building? Do you know what time is that?
I believe the email.
Yeah.
You didn't get that email.
Probably be an interesting meeting to attend if you plan on becoming a scientist or a chemist.
Yeah, I really wanted to go to that.
Probably be a little bit of good information about what kind of hazards exist in buildings that have been having chemistry done in them for years.
I think
So we
it
done with
was.
this guy?
Yeah.
So this one's a little confusing, I have to apologize. This total age of formation includes, or delta age of formation includes the formation of 3 moles of CO2 and 4 moles of H2O. And so this number, the negative 2,323 kilojoules, is the sum of the age of formation of 3 molecules of carbon dioxide, 4 molecules of H2O. It's already kind of added together for you. But the point here is that relative to this energetic altitude, formation of carbon dioxide and water, 3 moles of carbon dioxide, 4 molecules of water, releases 2,323 kilojoules of heat. And so we said that our H knots of formation is equal to H of the reactants minus the H of the products, the H of the products minus H of the reactants. And so for the elements, that goes to 0 in their standard state. And so the total H of formation of all of those compounds is simply that delta, which is, for this guy, 2,323 kilojoules. So the total H of formation of those compounds, which end up being the products, is that 2,000. Our reactants are below their reference elements by negative 103.9. So the total delta H of the reaction is products minus reactants. And that's going to be the negative 323, what was the last number? Or 230, or 2323. Minus the negative 103.9. So whatever 323 minus 103 is, it's 200 and, what'd you say it was?
2,219.8. Whatever we got.
2,219.8 kilojoules per mole. So we defined the enthalpy of that reaction based on the enthalpies of the products and reactants relative to their elements. Go ahead.
You said that was 0 over there, the reaction.
So, and whenever we have a reaction, and we're looking at the change in the enthalpy of that reaction, we take kind of the enthalpies relative to a reference. And so the total enthalpy content of any precursor is the change in the enthalpy when you produce that precursor from its elements. So up here, what I'm saying is, when we put this little F there, we're saying H naught of formation, and that means the enthalpy associated with formation of that compound from its elements in their pure states. And so for this sum, the enthalpy of the elements in their pure states is always going to be 0, because we just defined that as a relative altitude, an energetic altitude, right? And so the H naught of formation of any product is going to be the enthalpy, or the magnitude of the enthalpy change when you form that product from its reactants. You define the reactants as 0, so it's just that. If we're looking at our products and we're saying our products are 3 CO2 and 4 H2O, then the H naught of formation of those guys is the difference in the enthalpy when we form them from the products. So to calculate that, what we'd have to do is take the elemental precursors, throw them together in a reaction mixture, measure the heat change when they react, and then whatever the magnitude of that heat is, that tells us what our enthalpy is. Heat under constant pressure conditions. So we've defined that if we form propane and oxygen from its elements, we're releasing 103.9 kilojoules. If we form 3 carbon dioxide and 4 water from their elements, we're releasing 2,323.7 kilojoules. Therefore, if we form 3 carbon dioxide and 4 water from propane and 5 oxygen, the change in the enthalpy between those is going to be the difference in the enthalpies of those guys relative to their elemental precursors. See a lot of confused looks. Hopefully there won't be so many confused looks the next time I do this lecture. All right. So essentially, the take-home message then is that if we want to figure out the changes in enthalpy for any reaction, what we need to do is we need to figure out where the products and reactants of each reaction are relative to their elements, right? And so if we react their elements together to form all the different compounds that we're interested in, and measure the enthalpy changes associated with those, we can form tables like the one we showed here, where we've got tabulated values of all of these enthalpies. Enthalpy information of the cyclopropane, plus 53.3 kilojoules per mole. That's saying that if we take elemental hydrogen and elemental carbon and we react them to form cyclopropane, we're going to witness that we have to absorb 53.3 kilojoules of energy. So what you can do then is go out and tabulate all of these energy changes associated with the formation of hundreds, thousands of different compounds. And then anytime you want to figure out what the energy will be, the energy change will be when you go from one compound to another, you simply subtract those formation enthalpies, products from reactants, and that's going to tell you what the enthalpy change is when you move from one to the other. This is easier said than done. We're going to look at an example of why that's so. All right, so let's say that we want to calculate a standard enthalpy of formation of propane, or not propane, ethane. We want to figure out the enthalpy of formation of ethane. And we said that we're assigning a relative enthalpy, the enthalpy of that compound when it's formed from its elemental precursors in their most stable condition under 1 atmosphere of pressure, 298 Kelvin. And so what we'd have to do to make ethane is we'd have to take 2 moles of graphite and 3 moles of hydrogen gas and react them together and form our ethane and measure the enthalpy change of that reaction. And then we throw that enthalpy value up here on our table and we say that's our enthalpy of formation for ethane, and then we use it in any calculation we want to use down the road, right? The problem is if you take 2 moles of graphite and 3 moles of hydrogen, you throw them in into reaction together, they're not going to react. It's very, very, very slow reaction. Probably have to catalyze it and or, pump some heat into it to get it going. And even if you got it going, it's going to be very difficult to form just one reaction product. You get a bunch of different reaction products, and so that the heat